Welcome back to High Performance Computing, our lecture 1. Today, we're talking a little bit about the overall idea what HPC is, how we define high performance computing, what is a supercomputer. These are all elements you have seen basically in the part 1, and this part 2 will going a bit more broad, and we'll also think about that HPC is not just technology, it's actually much more. And the ecosystem is incredibly important. But part 1 was really thinking about a lot of technology elements, architectures, where we said there's basically shared memory, there's distributed memory, how we program them with OpenMP or MPI, the message passing interface. Of course, these are all elements which are not directly obvious to you, and we will see how that materializes in subsequent lectures when we really talk about MPI programming. But it gives you a reasonable good overview what HPC entails. And one of the important part was the interconnect. We have seen it also in the modular supercomputing VIDIA, Mellanox, and is really incredibly important as one of the provider of good interconnects today. And as such, HPC is really to be differentiated a little bit from high throughput computing in the sense that these systems are very tightly integrated, still modular, as we have seen in the video, with already considering potentially quantum devices and neuromorphic chips maybe in the future. And essentially, many of these topics were based on parts of theory. So when you think about parallel processing, you will think like always adding 2 more cores, 4 more cores, 6 more cores will just double the performance here and there, and it will be faster, but that's not the case. So we will see in subsequent lectures that actually parallel performance is then also limited by its, let's say, serial aspects. Things like Amdahl's law will be discussed, where we see it's not that easy. And even if you come then to this hybrid programming where people combine shared memory with distributed memory programming, it's incredibly hard to do so. So you need performance measurement tools, you need performance analysis to understand your codes better, to understand the mapping of the real physical HPC machine better, and with this also solving performance bottlenecks. And these are all lectures. When you now think and reveal again and go back to our outline, these lectures will come one by one. Finally, as a review of part 1, I just want to stress the importance of applications. I think you have noticed from the video maybe a little bit where the earth scientist was really speaking, Sabine Griesbach here, talking about really impactful simulations of Earth phenomena. And this is one of the idea of how you use HPC. And the reason is that you really cannot do that on a laptop on that scale to really understand it. It includes weather forecast, understanding the climate in more detail. But also, as we have seen in other slides from me in part 1 earlier, we talked about Formula 1 racing. We talked about Airbus as an example of, creating perhaps an aircraft and the idea how to do so. And we will pick that up in subsequent lectures. And that's why the second half of the course, as I noted also in the prologue, is so important to talk about applications, because the chances are when you endeavor in the field of HPC, it will be under the umbrella of an application. So usually people in HPC have either a completely technologist role maybe, but also many of those that are embarked on the journey of HPC are experts in physics for some specific area in science, let it be computational physics, computational fluid dynamics, let it be basically the earth sciences we basically have seen in the video. So long story short, applications are also incredibly important. All of them stress different aspects of the HPC systems. They shape the systems differently. That's why they are used also these days all for co-designing the next generation of HPC systems, because we want to know how we can best solve applications. We've seen the benchmarks of top 500, which is more or less, if you want, between us and the world here, still some conflict in the field of saying how very useful is that. So you would say a top 500 system is perhaps very good positioned, very high up in the list, but the real truth lies in the applications, and then taking advantage of a particular HPC system. And with this, they all have the different performance for different, application domains. And that's also what we will reveal at the second part of the course. So take away the message that applications are very important, and that's why we incorporate that also here in this HPC course. Now, another aspect of, let's say, elements which are not just hardware is something I want to convey now as part 2. When you're being in the field 18 years now, for me, you can imagine I've seen a lot of technologies. I've seen HPC hardware coming, going, filling a hole, basically hole, and then suddenly you're amazed that the same computing power can be filled in just a corner. And these days, even with energy efficient ideas of many core GPUs. So, but all of them are enabled by a so-called ecosystem. So you would say it's not only hardware, putting it somewhere in the cellar, putting it somewhere in a big hole. It's also the ecosystem that is enabling it and all the technologies that follow. So that is an interesting journey, giving a broader perspective. What is really, creating a HPC system, which is not just a CPU, it's not just a physical device lying there. And we have to really start by the system software environment, if you want the ecosystem of software. So a HPC system requires a good operating system. Sometimes it's actually a kind of reduced operating system that we talked about Unix, for instance. We would say reduced Linuxes could be one idea. There are different ways today. You would say scheduling systems. This is one of the most important tools, if not the most important tools, because you will see that a supercomputer is always shared, often with hundreds of users. In order to take care of the actions, who is allowed to compute where, how much space is available right now on a HPC machine. When I'm computing, because I want to be computing a lot, but there's no space, so I will be in a queue and waiting. So all these different questions will be something we call scheduling. And scheduling system like Slurm here, as an example, what we will do in the course are very important. IBM had their own system, load leveler. We have also seen other PBS and so on, other scheduling systems in the past, and all share the same idea of having really this kind of batch idea. So batch computing, you waiting in certain batch queues to be scheduled on these large HPC systems will be important. And the software is incredibly important to operate a HPC system. Hence, we will talk in practical lecture 1.1 directly about it. The next lecture will rightly start from it to understand better how you can actually share the concurrent access of a supercomputer and how you manage all of that. So with having lots of technology to integrate, you can imagine that monitoring these systems is also equally important. So here, system administrators, people responsible for the systems, they basically need to know, is it all working nicely? We have systems like Inca, Ganglia, and many others, LLView, for instance, in Jülich, that enable you to really see the system live and basically more or less like a heartbeat. So what application is running where? Is basically all the systems, are all the nodes, racks, CPUs, are they correct working? Is there an error maybe in a switch that deals with the interconnect? So all of this system load from applications, spanning all over the hardware, the so-called system load, if you want, is an important part as well. You want to make users happy. They should be, frustrated of using the system. So they assume that the system is running. In order to give feedback on those, we have monitoring systems, which basically are important to be also used in HPC system software. And then a couple of lectures will be focusing what I said earlier also on applications. So measuring the performance is not that easy. By doing so, you will identify certain patterns of inefficient behavior, like, for instance, wrongly sending messages, having a bad mapping to CPUs and cores, and many cores these days. So there are, let's say, a whole process of performance analysis with tools like Scalaska, with tools like Vampire we have to look in. And this will be covering not only, let's say, performance analysis, also the, let's say, idea of debugging, of profiling these applications. And with this, you have the four really big HPC system software, which is important to really make your applications working on the HPC systems. Now, a more emerging technology is more interactive. Now, interactive is a word which is interesting, which means it's not really this batch processing we just discussed. So you would say, like, I'm in the queue, I'm waiting. So why you suddenly talk about interactive? And this is, of course, for different application loads. So you have to see that the applications are all different. We discussed that already. You see here a very good example of the basically airflow through the nose. Here from a colleague of mine that is working on this, and basically then using interactive HPC to working in that specific environment. Also, we see the field of AI evolving very quickly, like machine learning, deep learning. These are all parts and lectures of the course, and we will discuss them intensively when we come there. But the key message to take away is that some applications are more done in an interactive way. While many people, perhaps 80% or 90% even, will use the batch processing, we have still new users and more, let's say, AI users that use interactive supercomputing. And there are approaches like the Jupyter notebook that you probably have already heard from, basically enabled also by a Jupyter Hub, which is a bit more sharing also for multi-users, different versions of notebooks, data, and so on. And what is also available to you. So that is something what we will use in the course. And some of you already are part of the big data and cloud computing course. So you have already used actually this particular technology, giving you basically more or less an interactive access to the supercomputer in order to use GPUs, maybe for cutting edge deep learning. And this is a more basically different approach that we will have to look at when we look at scheduling and so on, because this, of course, has impacts into the scheduling, how many nodes you will really address. And of course, this is something what we will also introduce a little bit in our practical lecture 1.1 to give you an essence of what that really means and how you basically can determine a little bit the difference of these both two approaches. Now, coming back to the HPC system architectures, this is basically very complex machinery. It's not basically an Apple notebook you buy, it works all the time, it's very easy, it's working with all your different applications. So here we bring together technologies of many different vendors. We have different CPUs, multi-cores, many different data access levels. Network topologies need to be combined. We have various interconnects. So basically these system architectures are relatively complex. We talk about lots of CPUs to integrate here and lots of cores to integrate in order to basically to get to one of the top 500 systems. So for the rescue, you see already a little bit what this picture is alluding to, that these racks and kind of these systems are more or less having a so-called blueprint, if you want, how they can scale up. So it's not that hopeless. So people have thought about these architectures. And basically, of course, we see a significant increase with performance. We basically see that GPU here and there, of course, have played their part. And now the GPUs and many core processors are really driving the scene, if you want. So in a way, you can see it as a revolution. In the last 18 years I have been in this field, GPUs definitely changed a lot of things. Also the libraries, the software that goes along with it in order to program on GPUs. And you see how that materialized when we talk about this in one of our coming lectures about, GPU programming and what is the difference. But essentially what I want to leave on the table is a little bit the idea of it's Formula One, and Formula One means cutting edge technology. And the one specific example I like very much to convey is essentially a supercomputer Blue Gene Q here. And you would say, some of the insiders in the community would say, well, that is, very old technology, but that's the point. So supercomputer Blue Gene Q was one of the best supercomputers in the world in the top 500, and suddenly just discontinued, right? It's a Blue Gene series building on L, building on P, building on Q, and suddenly stopped. But also we have seen the advancements of L, P, and Q before. So essentially you see that the whole system architectures evolve so quickly and suddenly maybe completely discontinued. And this shows you a little bit this risky business. It's not complete risk in the sense of lives, but here we're talking about, is the computer running? What is the strategy of all these different application scientists using it? And tomorrow we have to shut it down, and a new technology, maybe from Cray, from HPE, or maybe from Atos in Europe will come over, and basically we have to change maybe here and there our low-level aspects of this application. And another thing that I want to convey with this big picture here is the infrastructure. We talked about the ecosystem, right? So not everything is what you see here, this complete metal. When we basically are in the course, I told you already in the prologue, we also will touch metal together. We will hopefully, if COVID allows, go to one of the supercomputers so that you can really see how the CPUs are tightly integrated into the node boards and so on, and what constitutes a rack and so forth. But another thing is really the infrastructure around it. You see in a big, large supercomputing center, something like this big hall. And this big hall is protected, of course, by fire protection mechanisms, but those are basically not based on water. So it's based on gas. Of course, with this sensitive technology, you don't want to expose it to water. Another example is the floor here. We talked in the prologue already. This is the second floor. So lots of the network interconnects are actually hidden here down in the floor. And there are lots of other aspects which are all having more or less architecture impacts. Today we have warm water cooling, things which are not obvious to you, but actually what we will talk about in the course as well. So what I mean to say is the architectures will always change, right? But some of you maybe know that when you have videos from 15 years ago, 10 years ago, 5 years ago, in a way you have always this rack business. It is related a little bit to cooling. It's a bit related to the infrastructure of networking, but we will see how that materializes when we come to subsequent lectures. So HPC in the end, even if it reinvents himself always, perhaps every year, we see that, of course, some of them are moving very fast, but we have some aspects which are more or less the same throughout. So in order to create a system, and you would say 20 petaflops is very much in the past, it was Blue Gene Q technology. In order to create a system, it was built on racks. And when you go back in history with a Blue Gene P, the same was done in that area. And this was basically going then, of course, from different midplanes and node cards, compute cards, to the original chip in the end. And the similar system was like this. So I think the slide still carried around the message how we do it today. Of course, today we have also interesting technology alongside it, this accelerators we have to talk about. So GPUs is not anymore so homogeneous. And that's what I also want to convey in this slide. That of course the evolution is an interesting term, although we see still lots of these racks existing, and almost all supercomputers would have these racks these days. There's a smallest basically difference when they come to quantum devices. They look different, but basically here we have an interesting way of seeing all the different supercomputers in this racks, in this common terminology, if you want, with CPUs, with node cards, midplanes, rack systems, and so on. And of course, the interconnect, which is always a little bit hidden, perhaps, but which also contributes, if I may go back for a second, the network connectivity often to this shining nice lights. And when they're blinking hell a lot, could be storage, of course, the access to hard disk, or how much a compute cluster is used. But in many ways, it's also sometimes a network interconnectivity. And speaking of which, and we'll talk about this, of course, in one of the subsequent lectures much more, we said the network topology is incredibly important. Here we see one example, again, switching the view. from essentially the CPU-centric to network-centric. And in this network perspective, you have different networks like the 5D torus, trees, meshes, which enables you something what all these applications in a way or another somehow require. And that means nearest neighbor communication. So you want to have always a good connection to this neighbor. And if you are at the edge of the cluster, you maybe want to have a very good connection again to the beginning of the cluster. So, and we have some applications where we will talk about this in this course. Of course, obviously, with many users and multi-users, it is not so easy to map that all differently to all these different applications. And in a way, these large systems today have also several different IO nodes. They have different files they have to deal with. So IO is also an important part. So you think a little bit about, we can increase a lot in compute. And also our, let's say, systems capacity is growing. But what we face more or less today in HPC and a couple of years ago already is this IO bottleneck, essentially. So thinking about that, in a way, we basically cannot fuel quickly enough here and there the CPUs, and more is true of the GPUs today, which always have to go through the host CPU. So these are really limits in computing, more or less. It's much more, if you want, data limiting than compute limiting today. And with this, we probably have also very interesting ideas in the future how we can actually interconnect those devices. And then when you think about continuous developments, 20 years ago, nobody was talking about a GPU. People were maybe talking already about the so-called FPGAs. I would say there's some so-called field programmable gate array. In other words, you have, let's say, reconfigurable wired interconnects on these chips, and there were cell processors coming along. And suddenly the GPUs, which were intended for, let's say, much more graphic processing, were basically suddenly becoming mainstream processing. So GPU, general purpose graphic processing units arise. And this shows you in another interesting way how HPC really evolves. It became so quickly mainstream that FPGAs become a little bit, let's say, a side topic. So GPUs are really on vogue. They are incredibly useful for deep learning and for many other scientific applications. And we will see also in the modular supercomputing, it has a footprint. But it shows you also how lively this technology is with continuous developments, continuous improvements. It's not stopping at these a few that I show you here. As I said earlier, basically, we are talking about quantum devices we are already programming now, and there are neuromorphic devices on the horizon. So next modules to be integrated on this. And one of the key drivers really, where we will in lecture 9 look much more how accelerators really changed a lot of business in HPC is really the GPU. Of course, it's very NVIDIA dominant these days, but we will see also like the LUMI system in Finland, a supercomputer where Iceland is part of. It will also essentially enable us to see that there are different technologies and definitively new providers, which also provide accelerators in the future in order to have the same approach. And by large, you see the approach a little bit here alluding to many, if not thousands and hundreds and thousands processors, which are all, let's say, moderate thread performance. So I talked earlier that a single thread performance with very high single thread performance cannot increase much more on the chip because the heartbeat on the chip will be too much creating heat. And with having this moderate performance, you can basically put a lot of processors on the chip because the heartbeat, this is moderate performance, will be not as hot as the high heartbeat in gigahertz, but basically it will be moderate, and with this, the temperature will be still okay. The main trouble, however, you have with those GPUs is they're incredibly useful for, let's say, having lots of similar tasks operated on many moderate processors, but they always have to go through the device memory more or less to go to the main memory and CPUs. So there's still kind of a bottleneck these days. People have worked around it with GPU direct interfaces. It's what we do in research a lot and so, but still this bottleneck exists. However, it is a many core architecture which has stood the test of time and is by now also heavily integrated in the top 500 list. If you look basically on the best #1 system in Europe, you will find lots of A100 NVIDIA inside the Jewel system. And this, of course, provides a lot of performance while being very energy efficient, which is another important part. But it just turns out that many applications, if you will, can use this GPU acceleration brilliantly. And we will have a whole lecture 9 around it. I just want to bring you a short example that when you do it in a way that humans can understand it, a typical matrix vector multiplication, you already see the nature of this, that basically in order to perform this matrix vector multiplication, you see this color coding, you can directly imagine that essentially it can be done in a nicely parallel way. So alluding a little bit to the HTC that I was going through. So here we talk about throughput of a GPU. So this can be computed completely independent of essentially the other parts, right? The colors are only the ones you need in order to have this matrix vector multiplication. And with this, you can imagine that matrix multiplication, matrix vector multiplications are incredibly good to be done on GPUs because they don't have an interconnect, but they don't need an interconnect in the end with all this multiprocessors. It's very simple operations. If you know, here we just ended up basically by multiplying one column here really of a matrix with essentially one result element in the vector. And with this, basically you have a very simple interaction and you can copy paste this more or less in all the different matrix entities. So, and this is useful for a GPU to do. And we will see how that materializes when we talk also then in subsequent lecture after lecture 9 about deep learning, doing essentially nothing else than a hell of a lot of matrix multiplication and tensors and so forth. So there are lots of threads tackling in a very highly parallel and nicely parallel fashion a problem. And you see that most of the top 500 supercomputers have an accelerator of sort. So speaking of one part of the lectures, we discussed already the deep learning. This is in the area of artificial intelligence. You see here the example of actually having an image and then understanding with AI methods, machine learning, essentially to understand with neural networks what actually image is in terms of numbers shown. And in the past, there were perceptrons, as you have seen, very old technology from the 50s, really, that worked over the time. We will see neural networks with more hidden layers. And essentially, those were very good and could be computed with CPUs, and large neural networks were still able to be basically computed. What changed a bit the picture were the arising of deep learning. And actually, in deep learning, the innovation is really through specific layers and architecture types. And we will see that now in the video. And then I will summarize on it and make the point why high performance computing is so important. So let's look how the world changes from typical perceptron, which is a key part of a neuron in a neural network. And it's clear that this is not obvious to you. We'll see how that materializes in lecture 10. But then also how the old situation switched to deep learning, requiring much, much more computing power. And the video shows you nicely the differences. So we will have a whole lecture about it. There will be some practical lectures about it, also from the field of remote sensing, for example. But the point is really that from all the interconnections, some of you know that neural networks are built on the blueprint of the human brain, and we will learn about what a neuron is, what the interconnections are. But all the meshes you have seen in the video mean essentially training weights, training interconnections. These are done with multiplications of matrices, multiplications of vectors and matrices, but in the end require a lot of computing. And with this computing requirements, we have seen lots of these being interconnected, but also seeing the jump then to the so-called convolutional neural network. So a multi-layer perceptron is an artificial neural network, more or less what we call shallow networks. But the convolutional neural networks, which are able to work on images, are different scale, basically, and this is important to realize. So deep learning is not just putting deeper and deeper neurons. It also has specific layers, as we see here with feature maps, then really carving out the features of the different numbers instead of having plain neurons just basically interconnect. And we will talk about in lecture 10 about it, like also then these deep learning applications where we use, for instance, satellite images in remote sensing a lot, where essentially you put in a whole cube, and in order to understand what each pixel constituted, so is it the forest or river, you need lots of computing to train such a system, but then also to use such a system for having basically the probability, and could be like 58 classes you have of land cover from a satellite picture to understand what is it. And you see also the block behavior, which are different spectrum channel of lights. And in this sense, also the idea of why we need lots of computing power in order to compute this. And then there's a trouble of different parameters that basically will these also entail these lectures, and we'll discuss a little bit about these different parameters, let alone the big data coming from the satellites themselves. It will be all material of lecture 10. Where we discuss in machine learning and deep learning. So just a summarizing element here really of bringing things together. So the more computing you have in terms of these deep learning networks, the more basically you need the supercomputers. The shallow basically neural networks, but also support vector machines, random forests still have the state of play when the data set volume is relatively low. But if you want to really scale towards big data, you come quickly in the problem of MATLAB, statistical computing, and so on typical laptop machines will be running out of memory. So essentially, you need then the jump to high performance computing, to cloud computing in order to solve those problems. And the cloud computing already told you a little bit about scaling up with cloud technologies. There are technologies like Apache Spark, where you can maybe run different deep learning networks. Here's an auto-encoded deep network that you can use, and you have these worker nodes, and they may work not being completely tightly integrated. They can work nicely in parallel in order to solve a problem. But in HPC, we want to use much more, let's say, there's this tight connections, and also having lots of memory in some of these systems. And one of the memory requirements you see here coming out of an earthquake simulation from San Diego, where basically a terashake on this domain and a petashake, as we call it, with different mesh sizes and mesh point sizes, will also require the jump from terabytes to petabytes. And of course, this is a highly interesting challenge, because now the question remains how we work with IO in this particular manner, right? It's not only computing. Here, the bigger data for better accuracy of these earthquake models is, of course, also giving us a challenge of much more data. And this is also something we will talk in the course, although there's a so-called DRAM gap that basically means that in the moment we have more or less a problem that the main memory basically is very costly and the cache is much more. But in order to have essentially here something transported from the cache hierarchies back to main memory is this DRAM gap. But then also thinking about that many of the systems are memory bound, so we could use much more memory in these systems. And then you go to much more slower technology for, like here you see a disk array or even tape archives, which of course have lots of capacity, right? Main memory is, let's say, always limited. But here we have lots of capacity. They are very slow compared to main memory. There are also, of course, not so costly, that main memory, so we can have much of those, but still there's a discrepancy of this storage hierarchy, and we will talk throughout the course as well about it. So people have then tried to really do more or less hierarchical storage management in so-called tiers, and one of the first was here this gray wolf, where you see you have some different hierarchies of a server, all have their different capabilities. Let's say low memory in the tier 1, and then you have lots of those because memory is not so, it's very costly, so you cannot afford many of those. And then you basically increase with over the tiers with the importance of systems with a memory footprint, and then maybe less disk size, which means you compute much more intensive on the important parts after going through all the tiers. And the storage hierarchy will be a loaded term. It is much more on vogue with the Maya project, one of the logos in the course, for instance. And we will pick up on this here and there throughout the course lectures. Just to show a little bit about the application co-design of HPC, so modular supercomputing we discussed. Here the idea is, as we have seen in the video from part 1, being co-designed by many applications, we know now that some of them have different requirements or would use different parts of the cluster at different times. And the prologue already was basically looking a little bit into this. We have this cluster module, the extreme scale booster, data analytics specialities, but an application maybe requires some of those modules together, like the Klima workflow we have seen in the video, basically of part 1. And the same could be actually true for deep learning, maybe using parts of the quantum annealer for optimizing the optimization in deep learning and so forth. So it is enabling a much more flexible design, like the basically video suggested. And here in Iceland, we're working with this. We also have lots of context here. And I think that is also an important part of the ecosystem. Never underestimate the people working on the HPC systems. They have experience in their different domain of science, which complements neuroscience, remote sensing, natural language processing, health, medicine, CFD. They all have their different role to play, and it's a very important part of the ecosystem to be successful, to have good people. So simulation data labs is what we do in Iceland to really bring out the capabilities, to expertise, to nurture the environment in the sense of bringing it closer to the users, of really building a HPC community that stands together. We derive this strategy from the Jülich Supercomputing Center, creating #1 center of Europe right now in terms of the software and system. But of course, never forget that the system center, so to speak, also has lots of good people in the back that also contribute to this success. Only the good people and the application specialists and technology specialists really are able to make the best out of the systems. Hence, I also included here. And we have this National Competence Center here for HPC and AI in Iceland, which knows these systems very well from different angles of the different domain sciences, as you see here. And it's basically part of the EuroCC project. So you see this HPC community building is happening in all the different countries. So in the Euro HPC joint undertaking, this is something where basically we will see in the future a much more stronger movement as one from the European membership countries, the EU, but also of course EEA, and Iceland as an EFTA state, as an EA partner, is closely alongside those. We are a member of the Euro HPC joint undertaking. I'm the governing board member even of this Euro HPC joint undertaking. That's an exciting time. We have seen many different infrastructures in the past, which should not be forgotten. We have seen CERN with the grid experiments, which of course for district computing is a very high success. We've seen our US partners with XSEED Extreme Engineering Discovery Environment in the US being largely the HPC and even beyond HPC infrastructure of choice. Europe in the past was really driven by the Partnership for Advanced Computing in Europe, and I have also a video for you with some of the applications running on the PRAISE HPC infrastructure with lots of HPC systems, that we are in the transition process right now in Europe towards the so-called Euro HPC endeavors, which is a 7 billion undertaking more or less of the EU member states, and EEA is contributing to with 7 billion for bringing, of course, Europe and HPC really into the mainstream, as I would call it, more applications for the Digital European projects, programs. We have Horizon Europe, Digital Europe, Connecting Europe facilities, different programs with all different money. But in the end, they all should serve different user communities. So it's not all about just hardware. It's about software, it's about applications, it's about the skills of these people in all these different user communities with center of excellences. I will also show you when we talk much more in the subsequent lectures then here and there about applications. And with this, we basically done with the lecture now. I would like to play another movie from PRAISE right after I introduce quantum computing. This is really a very advanced concept. You could see in the modular supercomputing world as being one of the modules as an extension where you solve maybe different optimization problems. You see a support vector machine that we already use in some of our publications in remote sensing to differentiate the land cover of the Earth. And it has different principles. It's not only a lot of zeros and ones anymore. Essentially, when we talk about quantum computing, we have 0 and 1s at the same time. It's called a superposition of a qubit. And essentially, you're connecting those in order to solve problems. And it's a different philosophy how you compute really computing, but it is very related to high performance computing, and that's why I included it here. If you want to know more, obviously it's a very advanced technology. We cannot do much of that in the HPC course for master studies. But if you want to know more, I also gave here in Iceland a keynote at the UT Messa in 2020, which is available on YouTube here as an example. Or look at some of our recent applications on this with some publications in remote sensing, how we use a so-called D-wave quantum annealer, very specific form of a quantum computer, but it's already existing. And now it's really time to go to PRAISE, to also think about PRAISE as one of the key infrastructures in Europe in the last decade. And we will see how that now materializes when we go to the Euro HPC endeavors. It's a little bit a longer movie, but it has very nice application parts in it. So enjoy the movie and you see us afterwards.
High flexibility, great endurance, unprecedented accuracy, unmatched strength.
High-performance computing is like all of the big instruments of science combined into one. So it's a telescope that enables us to view the entire universe. It's a microscope or a particle accelerator which enables us to explore the quantum world of the very small. It's a reactor that enables us to study plasmas and what's going on in the interior of stars. And it's even a time machine which enables us to recreate the past or to predict what's going to happen in the future. Almost all of the major challenges that society faces, whether it's preserving our environment, improving our health care, or rebuilding our economy, are underpinned in some way or another by high-performance computing.
By pursuing our dreams or looking for new perspectives, we test our instincts, abilities, knowledge and spirits that regularly go beyond physical boundaries and intellectual understanding about the surrounding world. Developed out of necessity for future scientific and engineering discoveries, supercomputers are recognized as an indispensable research instrument. However, supercomputing can only aid in the battle for finding the answers to long-standing questions that have excited human curiosity from its very beginning. These and many other questions constantly push us to observe and ask more about the world around us and beyond what our eyes can see. Building these investigations around models, we get simulations and new observations, bringing new explanations based on the collected evidence. Equipped with the most powerful supercomputers, today's scientists and researchers have the potential to deal with the complexity of the phenomena by gathering new results and findings leading to further refinement of their initial ideas. Applying a comprehensive explanation supported by many facts and data gathered over time, and generating new hypotheses to predict yet unobserved phenomena. Ultimately, supercomputers allow the hypotheses of our greatest minds to be explained or even rejected when compelling contradictory evidence comes to fact. That's because supercomputing brings an unmatched combination of computational capacity and capability, which undisputedly strengthens the solid foundation of observation, experiment, and confirming evidence.
So that was really I wanted to bring on today. So here is the lecture bibliography, and thank you very much for joining today. We will actually continue with practical lecture 1.1 in the next time. So see you then.